There's a beautiful relationship between the period and the frequency of a wave. Let's do example 1 so that I can show you what we're talking about. So example 1 here, as you can see, says, what is the period of a wave of frequency 10 Hz, right? So we're looking for the period, which is denoted by capital letter T. So to answer this problem, we're going to use this second equation here. If we go ahead and do that, we're going to have T being equals to 1 divided by the frequency. But we know fully well what the frequency is. The frequency is 10 Hz. So we're going to have 1 divided by 10, which is equals to 0.1 seconds. The SI unit of period is seconds, as the period is the time taken for 2 cuts to pass a point. And then in example 2, we do it the other way around. What is the frequency of a wave with a period of 0.5 seconds, right? So now we given the period, it is said to be 0.5 seconds, right? And we're looking for the frequency. So we're going to use the first equation, which is F being the frequency is equals to 1 divided by the period, right? So we're going to have 1 divided by 0.5, which should be equals to 2 Hz, right? So the frequency of a wave with a period of 0.5 seconds will be 2 Hz. That's how you sort of move from period to frequency and from frequency to period. Let's go ahead and solve some more problems and see what we have. We know fully well that the distance between 2 successive crests is 1 wavelength. The distance between 2 successive crests is 1 wavelength. As a consequence, in a time of 1 period, the wave will travel 1 wavelength in distance, right? And then from there, we can deduce that the speed of a wave will be equals to the distance traveled divided by the time taken, which is the wavelength divided by the period. But without complicating things for you, we can also say that the speed of a wave is equals to the wavelength multiplied by the frequency. This is also true. So the speed is the wavelength divided by the period, or the wavelength multiplied by the frequency. We can also say that. And then in example 3, when a particular string is vibrated at a frequency of 10 Hz. So at this point, we know that we have a frequency which is equals to 10 Hz, right? A transverse wave of wavelength 0.25 meters is produced. So we have a wavelength of 0.25 meters. Determine the speed of the wave as it travels along the string. So we have a frequency and wavelength. Which formula we're going to use to find speed? We're going to use V as equals to the wavelength multiplied by the frequency, right? How do you know which formula to choose? It depends on the information you're given. So if we go ahead and substitute here, we're going to have a wavelength of 0.25 and a frequency of 10 Hz. And if you compute that, you should get 2.5 meters per second. A cork on the surface of a swimming pool bobs up and down once every second on some ripples. So the key phrase here is once every second. So that should tell us that we have a frequency of 1 Hz as it bobs up and down once every second. And then the equation goes on to say that the ripples have a wavelength of 20 centimeters. So we have wavelength being equals to 20 centimeters. But we know that we use meters and not centimeters. So we have to convert from centimeters to meters by simply dividing by 100, right? So the wavelength is now going to be equals to 0.2 meters, right? And then if the cork is 2 meters away from the edge of the pool, how long does it take a ripple passing the cork to reach the edge, right? So we have a distance which is equals to 2 meters, the distance from the cork to the edge of the pool. And then how long does it take a ripple passing the cork to reach the edge? So we want T, right? which is the time and not the period. Let's not confuse capital letter T and small letter t. So let's go ahead and see how we can find the t. So we know fully well from motion in one dimension that the time is equals to the distance divided by the speed, right? But then we know fully well what the distance is. The distance is 2 meters, right? 2 meters from the edge of the pool. So now we just need the speed, and we're going to be able to determine the time taken. So we're going to have speed being equals to, we given the frequency and the wavelength. So which formula we're going to use here? We're going to use wavelength multiplied by frequency. So what is the wavelength? The wavelength is 0.2 meters, and the frequency is 1 hertz, right? So 0.2 multiplied by 1, that is just equals to 0.2 meters per second, right? So if we substitute it here, we're gonna have 2 divided by 0.2. So what is 2 divided by 0.2? 2 divided by 0.2 is 10 seconds, right? So the time it takes a ripple passing the cork to reach the edge of the pool is 10 seconds. You can see that this question is a bit complicated compared to the ones we were doing, but it's still pretty much doable, right? Let's move and see what else we have. So we have example 5, which we have a diagram even. This is a past exam question. The question is saying that water waves crash against a seawall around the harbor. 8 waves hit the seawall in 5 seconds. The distance between successive troughs is 9 meters. The height of the wave from the trough to the crest is 1.5 meters. Okay, and then the first question, how many complete waves are indicated in the sketch, right? We can sort of think of a wavelength as 1 complete cycle, right? So if we start here at A, and then we keep going, then at this point we're gonna have 1 wavelength, right? Why am I saying though? Because this half and this half will give you a complete cycle, right? Let me just shade it so that it becomes more clear. These 2 halves will give you a complete cycle, so that is a wavelength. And then from this point going to this point is another wavelength, because this half and this half will give you a complete cycle. And then from here, if we keep going up to this point, we're gonna have another complete cycle, right? Let me just wave it, let me just shade it so that it can become pretty much clear. So you can see here from our sketch that we have 1, 2, 3 complete waves. So the answer to A here is supposed to be 3, right? Now let's do B. B is saying that let's write down the letters that indicate 2 points that are in phase. Now the question is, when do we say that 2 points are in phase or 2 points are out of phase, right? 2 points are in phase if they have the same displacement from equilibrium position. 2 points are in phase if they have so the first condition, same displacement, right? So same displacement from equilibrium position or from the position of rest, right? That's the first condition. And then our second condition, we can only say that 2 points are in phase if they are moving in the same direction. So moving in the same direction, right? In the same direction. So if those 2 conditions are met, then we can say that 2 points are in phase. And then for out of phase, we have very similar conditions, but they're not exactly the same. So we have same displacement. So we have the same displacement from rest. Now instead of moving in the same direction, the 2 points are moving in opposite direction, directions, right? So let's go to a graph and see if we are able to identify that. So points that are in phase, let's look at B, right? So B here has the same displacement from rest as point D, right? And then they are moving in the same direction. So we can say that B and D are in phase with each other. Still at B, we can say that B and F are also in phase, as they have the same displacement from rest and are moving in the same direction. The same is true with D and F. So D and F, right? D and F, right? We can also go to the other points. C and E are in phase. They have the same displacement. They have the same displacement from rest, and they are moving in the same direction. Right, now let's go to out of phase. So let's look at B first. So for out of phase, we can say that B and C are out of phase. They have the same displacement from equilibrium, but they are moving in the opposite direction. So here we can have B and C, and then we can also have B and E, so on and so on and so on, right? Just like that. That's what we mean when you say 2 points are in phase or 2 points are out of phase, right? Can you just let me know other points that are out of phase in the comment section? I would really appreciate that. Now let's go to the third question, which is saying that let's write down the letters that indicate one wavelength. The letters that indicate one wavelength. So let me just clear up things on this sketch so that we can have a bit of clarity. So 2 points that indicate one wavelength, right? So we say that from A to this point, it's one wavelength, right? But then there's no letter there, so we cannot use that point. Let's use B instead. So from B to D is going to be one wavelength. The distance between two successive crests, right? Also the distance between C and E, we're going to have a wavelength. And then between E and G, we're also going to have a wavelength. Between D and F, we're also going to have one wavelength, right? So here you can write B and D. You can write D and F. You can write E and G, and so on, right? There's a couple of answers that you can write. Now let's do C, which is saying we should calculate the amplitude of the wave. So if we look at our sketch here, so let's just sketch a line of equilibrium so that we can have a bit of more clarity, right? It will make our lives extremely easy. So yeah, there we go, line of equilibrium. So the amplitude is the position from rest to maximum displacement. So this is what we're looking for, right? But then we know that from this point to this point is 1.5 meters. So the amplitude is supposed to be half of that, right? So if we calculate that, we're going to have our amplitude being equals to 1.5 divided by 2, right? So we have 0.75 meters. And then now D says that let's show that the period of the wave is 0.625 seconds. Usually when we hear period, we just want to say that T is equals to 1 divided by frequency, but that is not going to work with this question. But let's try to solve the problem and see what happens, right? In the question, we are told that 8 waves hit the seawall in 5 seconds. 8 waves hit the seawall in 5 seconds. But then the period is the time it takes for the wave to travel 1 wavelength of distance, right? So in this problem, we're going to say that the period is equals to the time taken, right, divided by the number of waves, which is going to be equals to 0.625 seconds, right? Let's do E, which says let's calculate the frequency of the wave. Now E becomes pretty much straightforward because we already have the period, right? We can just say that the frequency is equals to 1 divided by the period, which is going to be equals to 1 divided by 0.625, which is equals to 1.6 hertz. The last question, we're looking for the velocity. So let's look at the information we have. We have the period, we have the frequency. Let's see if we have the wavelength, right? We have the wavelength here. It is 9 meters. So we have a wavelength which is equals to 9 meters. So we can say that the velocity will be equals to the wavelength multiplied by the frequency. We can also just say the wavelength divided by the period. But let's just go ahead and do that. So we're going to have 9 multiplied by 1.6, which is going to be 14.4 meters per second. You should have realized that we've been solving problems that have to do with transverse waves, right, for the most part. Now let's talk about longitudinal waves, sound waves, and so on, right? So let's move ahead. So example 6 is saying that the musical note A is a sound wave. The note has a frequency of 0.4 kilohertz. 0.4 kilohertz. Let's underline that. And then it has a wavelength of 0.784 meters. Let's calculate the speed of the musical note, right? So speed is equals to wavelength multiplied by the frequency, or the speed will be equals to the wavelength divided by the period. Here we given the frequency, so we're going to use the first formula, right? So we're going to have the speed being equals to the wavelength, which is 0.784, and the frequency, which is 0.4 kilohertz. And we know that the SI unit of frequency is hertz and not kilohertz. So because of that kilo, we have to multiply by 1,000. And when you do that, you're going to get 313.6 meters per second. Let's move to example 7. So example 7 is saying that a longitudinal wave has a compression to compression distance of 10 meters. So this is a wavelength of 10 meters, compression to compression, right? It takes the wave 5 seconds to pass a point. It takes the wave 5 seconds to pass a point. So that is the period, right? So we have a wavelength, the period. The first question says, what is the wavelength of the longitudinal wave? Like we have already said, 10 meters. And then the second question, what is the speed of the wave? So speed will be equals to the wavelength divided by the period. So we're going to have 10 divided by 5, which is just 2 meters per second. And then now off to example 8. A flute produces a musical sound traveling at a speed of 320 meters per second. The frequency of the note is 256 hertz. Let's calculate the period of the wave. So we have the frequency, so the period should be pretty much straightforward. 1 divided by the frequency. So we're going to have 1 divided by 256 hertz, right? And then if you put that in your calculator, you should get 0.0039 seconds. And then now the second equation, we're looking for the wavelength. So we have the period, we have the frequency, we have the speed. So the wavelength should be pretty much straightforward, right? So we're gonna have the speed being equals to the wavelength multiplied by the frequency. So if we make wavelength the subject of the formula by dividing both sides by frequency, we're gonna get V divided by frequency being equals to the wavelength. So the speed is 320 and the frequency is 256, right? So our wavelength should be equals to 1.25 meters, right? That's what our wavelength should be equals to. Now the last question, you can stop the video and read through this information, but then for the sake of time, I'm just going to solve the problem. So a ship sends a signal to the bottom of the ocean to determine the depth of the ocean. The speed of sound in seawater it's 1450 meters per second. If the signal is received 1.5 seconds later, how deep is the ocean at that point? So let's conceptualize here so that you can see what's going on. So here's a ship, right? So let's say our ship is at this point. It sends a signal, and then the signal bounces off from the bottom of the ocean, and then it goes back up to the ship, right? How long does that entire process take? That entire process it takes 1.5 seconds, right? So it takes 0.75 to go down, and then it takes 0.75 to go up, right? And then the question is asking us how deep is the ocean at that point. So we know the velocity that the signal is traveling at, right? That is 1450 meters per second. And we also know the time it takes to go to the bottom of the ocean. It is 0.75 seconds, right? Or 1.5 divided by 2. That's how the 0.75 is coming about. Now we just are looking for the distance, right? So this will be easy to compute because we know that the distance is equal to the speed multiplied by the time. So we're going to have 1450 multiplied by 0.75, which will be 1087,5 meters.